Okay, so we did the first two topics that are covered on the final, or broadly, polynomials and rational functions. Then we move on to, not the ideal color there. Then we move on to exponential and logarithmic functions. And let's remember what, so let's start off with exponential. So for exponential, you've got base to some exponent equals an answer. And what do we need to know about exponential functions? Well, you should know how, if you have to solve problems like this. So 2 to the x minus 3 equals 4 times 8 to the 5x plus 1. Well, what makes it exponential? Well, there's a variable in the exponent, and being able to solve by writing both sides in terms of the same base. That's what we did before we had logs. And then we also graphed exponential functions. And in general, exponential functions, there is and this, of course, has exceptions, but in general, there's a limitation on the range. So if I look at this here, we've got the domain is all reals, but the range is 0 to infinity, and there is a horizontal asymptote at y equals 0. And remember that for an exponential function, the base has to be greater than 0 and cannot equal 1. And so that is very important. So the base, you can't have negative 2 raised to the x. You could have this, of course, but that is not a base of negative 2. This is the same thing as saying negative 1 times 2 to the x. 2 would be the base there. And we did also, so in addition to graphing and doing domain and range of exponential functions, we also did a lot of application problems in terms of exponential growth and decay. We talked about half-lives, doubling time, triple time, fourth life. So but in general, if we were talking about, let's just say 3 times 2 to the t over 5, well, this would be a doubling time problem where the doubling time would be 5. Now, I haven't told you the unit of time, so it could be 5 days, 5 years, you just don't know, unless it all depends on the context of the problem. But in general, if once you have the base here, if it's of the form t over some value, that value is whatever the amount of time the base is. So for example, if this was a half, then 5 would be the half-life time, the time it would take for the substance to be half of what it originally was. Other types of exponential problems that we talked about were interest rate. So we had compound interest, where interest was compounded a finite number of times. So it's equal to the original amount times 1 plus r over n, r being the annual rate, n being the number of times compounded per year raised to the nt. Or we introduced a extremely common base that you'll use particularly when you get to calculus, but is also used in a ton of scientific and statistical application problems, is base e. And so remember, base e is about 2.7, and again, common base, and it's the base of the natural log. But in terms of interest problems, we had when interest was compounded continuously. In other words, as if in the compound formula, n going towards infinity, in which case you had a equals p e to the rt. And then we moved on to logarithms. Let me just add a new page. So in terms of logarithms, we talked about how logarithms are the inverse of exponential functions. And so when we talk about, again, exponentials, we have a base, exponent equals some answer, whereas for a log, it's log base answer equals exponent. So, for example, if I had log base 2 of 8 equals x, this just means 2 to the what power gives me 8. And of course, that would be 3. So knowing how going between the two forms is very important. And then also we talked about, actually before I get to laws of logs, just the common log is log base 10. And that's just, I mean, you can write log base 10, but most people just write log x with base 10 being assumed, the common log. Natural log is log base e. And again, we don't write log base e of x, we write ln of x. In terms of if we were to graph a standard log function, the range, as long as you're taking the log of all positives, then the range would be all reals. But the limitation is the domain, because whatever's inside the log, you can only take a log of positive values. Remember, this is the inverse of exponentials. So with the standard exponential, you could not get a negative, like 2 to the x couldn't be negative or 0. So you would have a limitation on the domain here. It'd be 0 to infinity. But in general, and it has a vertical asymptote of x equals 0, in general, to figure out, I'm just going to write it like this. In general, to figure out the domain, whatever's inside the log needs to be greater than 0. And in terms of the vertical asymptote, if there is one, it's wherever inside the log equals 0. So that would be how you'd find the domain and the vertical asymptotes. And again, as long as you're taking the log of all positives, your range is all reals. If you're taking a subset of that, then your range will not be all reals. And okay, laws of logs. So there are 3 main laws of logs. Multiplication within a log goes to addition in separate logs. Division within a log goes to subtraction. B of A minus log base B of B. And the very powerful one, so 1, 2, 3, is that if inside a log, everything inside the log is raised to a power, that exponent can come out down in front, which is powerful because one way to solve for a variable in the exponent, if you can't make the base the same on both sides, is to take the log of both sides. And kind of a final along with that is the change of base. Like I can write a log in any base I want. So for example, say I have a log base B of A. Well, I can write that in terms of common logs, log A over log B, or I could write it in terms of natural log of A, natural log of B, or I could write that in terms of any base I wanted, log base K of A over log base K of B. And that too is a good way to manipulate and solve some log problems. And yeah, so we did a lot of examples with that. I think I'm going to stop that here.